Good morning, everybody. I will be talking to you about the hydrologic aspect of the project that Phil just talked about. This is about hydrologic modeling. And I will be telling you a little bit about the hydrologic modeling that we're doing, the methodology, and then I will give you some examples to show you the type of products that we are creating within this part of the project. The main motivation that I see for in this project is to have an estimate of how water resources in the region in the Pacific Northwest will change in the next 100 years based on the climate estimates that we have. And it's a very relevant question because previous studies have shown that there will be some changes. And so we're aiming at getting the best estimates that we can. In this integrated modeling approach, the flow of information is from the climate part of the group into the hydrology and the vegetation modeling. And so this creates a more congruent product at the end between the climate evaluation and the hydrologic estimates. There have been previous efforts, similar efforts to this in the past, in which climate predictions have been used to drive hydrologic models to estimate the hydrologic futures in the region. And there's this project has some improvements. Among them, we are using the latest generation of GCMs. We are using the GCMs have been evaluated, and we're using new downscaling approaches, in particular the multivariate, adaptive constructed analogs downscaling method. We're also using daily GCM data. In the past, monthly data was archived from the GCMs, but now daily data is available, so we're using that data in our simulations. And we're also using downscale solar radiation and specific humidity. These two variables before were estimated from precipitation, the daily temperature range, and minimum precipitation, and now we're using them directly downscaled from the GCM models. The output of our modeling will be, or it's 3-hourly and at 116-degree spatial resolution. And these results will be publicly available for others to use. Now, I will describe briefly the methodology that we're following. We start with climate scenarios for the next 100 years. And from there, those scenarios, we estimate hydrologic scenarios for the next 100 years. So we have about 20 GCMs and 2 emission scenarios. So we have a wide range of future scenarios that we're estimating. We have the GCM data, then we do downscaling using the MACA methodology, and we have to train that data. So we use some grid observations to do downscaling. For example, we're using this data set, Livnet et al. 2013. Once we have the downscale data, we run the model. For example, the variable infiltration capacity model, VIC, and we have to select certain model parameters to run the simulation. All of this will affect the hydrologic output that we get. The hydrologic output in itself is part of the product. In the next slide, I will describe some of the variables that the model is producing. And then finally, we can aggregate those spatial variables, flow routing, and estimate stream flows. The set of variables that we're dealing with, we have the climate variables that are the forcing into the hydrologic model, and the outputs. As you can see, there is a large number of input variables and a large number of output variables. The variables that we use to force the model are precipitation, maximum and minimum temperature, from which we can estimate the daily temperature range, mean wind speed, mean incoming solar radiation, and mean specific humidity. And the output variables can be divided into water balance related variables and the energy balance related variables. They include runoff, base flow, evapotranspiration, snow water equivalent, for example. The energy balance variables include latent heat, sensible heat, net radiation, etc. In the next slides, I will show you some of the output that that we're generating, and I will focus only on two variables, maximum temperature and evapotranspiration. The way I see it is we have this information about climate change, and the question is how does this climate change translate into hydrologic information or water resources information, and there are many different ways to look at the output, because there is spatial variability and temporal variability. So that's what I will try to describe a little bit more in the example. This example is of preliminary results of our hydrologic simulations, and they correspond to the CCM 3E GCM, to the variable infiltration capacity model, and I will be comparing a present scenario and a future scenario. The present scenario is for the period 1971 through 1999, and the future scenario corresponds to the A2 SRES emission scenario, and for the period of 2041 through 2070. So there are different ways in which we can look at the output, and I'm presenting, this is the first one out of three. One is that we can look at changes in climate and in hydrologic outputs on a climatologic basis. And by climatologic, I mean we're looking at how the mean monthly values of each variable change. We're looking at the mean monthly values for each variable. And here I'm showing 4 points within the domain. This map here shows the domain that we are working on for this project. It includes the Columbia Basin and the coastal drainages next to the Columbia Basin. So it includes it includes Washington, most of Oregon, Idaho, and part of Montana. And since we're doing a hydrologic modeling effort, we don't follow very much the political boundaries, but the hydrologic boundaries. And that's why we're including also part of Canada. And in this example, it's plotting the historic temperature for each of these points. And you can see the temporal variability. The temperatures are high in summer. You can also see the change into the future scenarios, into the future scenario that I'm showing as an example. There is temporal variability in the changes. The changes are higher in the summer than in winter, like Phil said before. And their changes are also different from point to point. And now the question is, how does this information translate into the hydrologic states once we run it through the hydrologic model? And there is variability in time. For example, most of the changes occur in these 2 months in this case, and there is little change in winter. And also there is spatial variability. There is a lot of change happening at this point, that is on the Olympic Peninsula, and there is little change happening at this point in eastern Washington. There's other ways in which we can look at the spatial variability in more detail. And in this slide, I'm showing changes in temperature from the historic period to the future period. And it shows that the temperature is estimated to change about 2 degrees in the coast, and then the changes are going to be larger inland, up to about 3.5 degrees. How does this temperature change relate to the changes in the hydrology, in specific in evapotranspiration? We see that the changes are not uniform. Most of the evapotranspiration increases by about 200 millimeters per year on these red areas that correspond mostly to mountains where there is more water. So it makes sense that as temperature increases, you will see higher evapotranspiration increases where you have moisture available. And finally, this is how stream flow estimates look. This is the historic outflow at this basin our historic estimate, and then this is a future estimate. And we see a shift in the timing of the peak stream flow at this particular basin. This is the type of information that we are generating, and we are trying to get the best information that we can within this integrated scenarios approach. The goal of this is to generate these scenarios for public use. The examples that I show you show the type of information that is being produced. And these examples also show some of the changes in climate and hydrology that we are expecting to see in the near future.